Sometimes it's useful to be able to break down acceleration into a component that's tangent to the curve and a component that's normal to the curve. These are referred to as the tangential and normal components of acceleration. To come up with what they are, recall that the unit tangent vector is equal to r prime of t divided by the magnitude of r prime of t. And using the notation that we've used in this section here, that means v divided by the magnitude of v. If we let a scalar v represent the magnitude of the vector v, then by clearing the fraction of this equation, we can say that the vector v is equal to the scalar v times the unit vector t. That's the unit tangent vector t. Let me move this up here because I just put that in a weird place. There. Now, acceleration is, of course, the derivative of velocity. And so we'd be looking at vt prime as an expression for acceleration. Using the product rule, we have v prime t plus vt prime. Let's set that aside for a moment. Since curvature is kappa is equal to the magnitude of t prime divided by the magnitude of r prime, the magnitude of t prime can be given as kappa times the magnitude of r prime by simply clearing that fraction. But using what we've written above as our notation here, we can then say that the magnitude of t prime is equal to kappa times v, the magnitude of the velocity vector. Now, set that aside for a moment. I swear we'll come back to these things that we're setting aside. Because the unit normal vector is equal to t prime divided by the magnitude of t prime, clearing that fraction gives us that t prime is equal to its magnitude, the magnitude of t prime, times n. Okay, now I'm going to start to put things together. T prime is the magnitude of t prime times n, but the magnitude of t prime can be replaced by k times v. And we have that t prime can then be written as k times v times the unit normal vector n, where we've simply replaced the magnitude of t prime by k times v. And folks, the point of this, being able to say that t prime is kvn, is that we're going to replace t prime in the acceleration vector that we came up with by using the product rule. So, the acceleration vector is equal to v prime t, we already had that part of it, plus kv squared n, where the v squared is coming from the fact that we already had v in front of t prime, and t prime is being replaced by kvn, so we have kv squared n. This was the point of the exercise that we just did. Now we have acceleration broken down into one component that's tangential to the curve, that's v prime t, and another component that's normal to the curve, that's the plus kv squared n part. V prime and kv squared are called the tangential and normal components of acceleration, respectively. I'm going to use some colors that I haven't used just yet. So v prime is the tangential component of acceleration, and kv squared is the normal component of acceleration. That's what's meant by respectively, of course. And they are denoted a sub capital T is equal to v prime, and a sub capital N is equal to kv squared. With this notation, we can write that a is equal to a sub t, oh that's the vector a sub t times t plus a sub n times n. Okay. Now, what does all this look like for a curve? Suppose we have a curve C, and on the curve we have a point. Say at that point there exists an acceleration vector a. At the point on our curve there exists a unit tangent vector. Give me just a second. That's t. And at that point there's a unit normal vector, which is orthogonal to the unit tangent vector because of work that we've already seen before. The vector a can be expressed as a linear combination of the tangential vector and the normal vector. So we have this scalar multiple of t, we'll call it a sub t, because that's, what we've just been working on. And we have a scalar multiple of n, we'll call it a sub n, n. And the acceleration vector is the sum of a sub tt and a sub nn. That's what this equation is saying, and this is the pictorial representation of what the equation is saying. We can develop formulas for a sub n and a sub t that depend only on r and its derivatives. In order to develop formulas for a sub t and a sub n that depend only on r prime, and r double prime, we consider the dot product v dot a with v equaling, well, the vector v equals vt, where the non-vector v is as before, and a is what we just came up with, v prime t plus kv squared n, where v is the magnitude of the vector v. v dot a is equal to vt dot v prime t plus kv squared n, because those represent our v and a. The dot product distributes over addition, and so this expression becomes vv prime t dot t plus kv cubed t dot n. Since the magnitude of t is 1, t dot t, which is the magnitude of t squared, is equal to 1. Since t and n are orthogonal to each other, that dot product is 0. We can clean this up then and say that v dot a is simply v times v prime, which means we can express v prime as v dot a over v. But in terms of r, v is r prime, a, whoops, I already have a written down. A is r double prime, and in the denominator, v is the magnitude of r prime. So, since the tangential component of acceleration a sub t is equal to v prime, we can say that a sub t is equal to r prime dot r double prime over the magnitude of r prime. And that's nice because to compute it, all we need is r and its derivatives. The normal component of acceleration is, we already discovered, kv squared, but one of the expressions for curvature, k, is it's the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. V squared is the magnitude of r prime squared, and so we're going to have two factors of the magnitude of r prime divide out. We then have the normal component of acceleration that can be expressed as the magnitude of r prime cross r double prime divided by the magnitude of r prime. This is kind of nice because now we have expressions for a sub t and a sub n that depend only on r prime and r double prime, and they even look similar. For a sub t it's a dot product, and for a sub n it's the magnitude of a cross product in the numerator, and both of them have the magnitude of r prime in the denominator.